All right, so this is a course on information geometry. And so Amari, who's one of the founders of the field, prefaced his textbook in the following way. So Amari sort of refers to information geometry as a method of exploring the world of information by means of modern geometry. And so one might ask, well, what does this really mean? And what role does geometry play in something like this? And I'm going to try to briefly motivate why it is that such an approach is, relevant, both in statistical inference and in machine learning, right? So the basic idea, if you will, is that there's this notion of a space of models, if you will. Okay, so we have a space of models. And typically it's like you think of these as probability distributions. And these models are then going to describe our best understanding of the state of a system which we're trying to estimate. So from which, and we use this to describe sort of the state of a system we're trying to understand, right? To sort of estimate or understand. Okay. And so, what are examples of something like this? So for example, in inference, right? I should say maybe statistical inference. What you have is that we have data, and from that we want to infer our best guess, basically, right? Of what that data is describing, right? So what that data is being sampled from, perhaps. So imagine, for example, there's some underlying distribution, some underlying probability distribution, and you sample from that, and from that data you want to infer what that probability distribution is, right? So that's one possible example. And something similar happens in machine learning, right? It's like you have a whole bunch of training data. It's like, and there's an underlying model. It's like what you're trying to fit that training data to. So, for example, if you have neural networks, deep neural networks, you can think of that as being some sort of parameterized family of models which represent some sort of input-output relationship or some sort of map, right? And you want to find, it's like the parameters, you want to tune the parameters in such a way that that map is, you know, it's like as accurately as possible reflects, it's like the data, the training data which you have. Okay. All right. So in both of these situations, you are basically trying to address some sort of best approximation type problem. So you can think of this as a sort of best approximation problem. Right? So you want to choose from the possible hypotheses, for example. If you want to think of points, it's like in this space, it's like as a hypothesis. You want to choose the hypothesis which best agrees, it's like with the data which is available to you. Or you want to choose, say, the best, you know, it's like deep neural network with prescribed parameters, which best describes the data. Okay? So in order to do that, what do we need abstractly? So you have a curved space potentially of possible models, right? And you have some sort of data, and you want to, you basically want to find what is the best model, it's like, you know, it's like of that data, okay? So, so geometrically speaking, this, the underlying concept that's like which is relevant is this idea of a distance. Sort of comes into play. All right. So again, in statistics, this might be something like the likelihood. And so in statistics, so this might be likelihood. And in learning, it's like this might be the loss function, right? So okay. All right. So, you know, it's like in most of the cases which have been studied to this point, what basically happens is that even if this space of models is somehow curved, what you do is that you pretend or you consider the case where they are parameterized by some sort of parameters, and you use the underlying, say, Riemannian, sorry, the underlying Euclidean geometry, it's like, which is induced by that parameterization to do computations on that. So what do I mean by that? So what I mean is the following. So imagine this space of models is some sort of curved space, all right? And to make life easier, let's assume that reality, or what you're trying to model, is a point on that curved space, okay? And your best guess is some other point on that space. So this is reality, and this is your best guess. Okay, and as you might expect, what the goal of inference is then, or of learning is to try to have that best guess approach reality. Okay, and of course, it's like if you are in learning, it's like you've clearly heard of things like gradient descent methods. So in learning, for example, right, we have sort of gradient descent methods. Okay, and so for example, if you have a loss function, it's like you might want to, it's like do gradient descent along the loss function in order to converge. It's like to your best guess. I mean, in order to converge to as close as possible, it's like to reality, given the data which you have, right? So, so in the context of gradient descent methods, we know how to do that. Obviously, it's like on flat sort of linear spaces. But one might ask, well, what is necessary to do something like gradient descent on a curved space? Okay, so to do gradient descent on a curved space, one needs some notion of what is called a metric, right? So a metric is something like an inner product, right? So this is which is an inner product, sort of which is a choice of an inner product at every point. I should say a smooth choice on the curved space. All right, and what that choice of an inner product at every point in the curved space allows you to do is to then measure basically things like distances along some sort of curve, for example. Okay. All right. So if you had a metric, then you can make sense of what it means to have something like the gradient, and then you can talk about things like gradient descent methods. If instead of doing gradient descent, you wanted to do something, it's like which converges faster, like Newton's method. So if we wanted to consider instead sort of something like Newton's method, then it turns out that just having this notion of a metric is insufficient. So we also need to introduce the notion of an affine connection. So you might ask, well, what is an affine connection? And at its essence, it allows you to talk about this notion of what's called covariant derivatives, but it also perhaps more intuitively allows you to do the following problem, right? So again, you have some sort of curved space, and imagine that you have a tangent vector at a point to that curved space, and you have a curve along that. Okay, so along this curve, what you would like to be able to describe is some way of saying that this tangent vector at this point is somehow equivalent to this tangent vector at sort of a nearby point along this curve. So basically, you want to say that as you move along this curve, it's like then this tangent vector is going to be parallel transported. It's along this. All right. So that parallel transport allows you to do a variety of things, right? For one thing, it allows you to make sense of one possible way of making sense of what it means to have straight lines in a curved space. So anyway, so this affine connection sort of induces sort of a parallel transport Okay, and that allows you one way. There are more than one way, but it's a one way of generalizing the notion of straight lines. Okay. So what do I mean by that? That you want to generalize the notion of straight lines. And let's maybe sort of think about intuitively what we tend to think of as a straight line. Again, it's like a sort of a flat linear space. Okay, so imagine you have now a plane and you have 2 points, right? And you want to look at a straight line joining those 2 points. So there's sort of 2 properties, it's like, which sort of immediately come to mind, right? One of which is that if the straight line joining these 2 points is the one where, if you look at all possible paths connecting those 2 points, it's the one which minimizes the sort of the length, right? So sort of 2 notions of straight lines, right, in sort of linear spaces. Okay, so one of which is this idea of length minimizing curves. Right, and as you might expect from our discussion earlier, if you want to adopt this idea of, the generalization of straight lines to curved spaces as a length minimizing curve, then the notion of the metric, it's like which we sort of briefly mentioned, is the relevant concept here. So on curved spaces, right, this relies on the notion of a metric. All right. So the other way to do this is that you're always moving in the same direction. So a straight line is something where so it is a line or curve which is moving in the same direction all the time. Okay, so all right, so what does that really mean? Okay, so imagine you have a curve like this. What does it mean for the curve to always be moving in the same direction? So if you have a parametrized curve, it's like then you have this idea of tangent vectors to that curve, right? So the intuition here is that you want to look at the tangent vectors of this curve, right? So look at the tangent vectors. And they should all be pointing in the same direction. Okay, so again, it's like with space, it's like the tangent vectors literally do always point in the same direction, so that's consistent with that intuition. But now you have a curved space, all right, and you have these tangent vectors. So what does it mean for these tangent vectors to be pointing in the same direction? And so we had just talked about this idea of an affine connection inducing this idea of a parallel transport. So as you might expect, basically what's happening is that you take this tangent vector and you parallel transport it along the curve. You get a bunch of tangent vectors. Well, you get a bunch of vectors with which are based at that along the curve, and you want to compare that then to the tangent vectors which are induced. It's like by differentiating that curve. And so if those two things agree, then you now then have a curve which is moving in the same direction, so to speak. Okay. All right. So anyway, so this is connected to the notion of an affine connection. Okay. So these are some ways it's like in which geometry shows up when you're working with, it's like what is going to be called information manifolds. So again, an information manifold sort of intuitively is this family, it's like of statistical models, probability distributions, what have you, points it's like on that information manifold correspond to a particular statistical hypothesis, say, and then you want to move on the statistical manifold in order to do inference, it's like, and to, it's like use the data as best as you can, it's like in order to get your best estimate, okay? And the point basically is that if you want to introduce all the usual notions, it's like which we have, it's like at our disposal for talking about moving, it's like, it's like towards, it's like some sort of objective or goal, then you're going to need these type of geometric objects like the metric if you want to talk about, length minimizing curves. You want to get from point A to point B as efficiently as possible. Or, it's like this notion of an affine connection and its associated notion of parallel transport if you want to always be moving in the same direction. Okay, so what's going to happen basically is that in addition to all these type of standard objects which show up in, it's like a fairly standard class on differential geometry and Riemannian geometry, we're also going to talk a little bit about what are called divergence functions. So I'm again just going to very briefly talk about it. So there's going to be this idea of a divergence function. And one way intuitively to think about a divergence function is that it's sort of a possibly asymmetric distance function. Sort of between 2 points on an information manifold. And I guess it's like I've been throwing around the word information manifold. It's like again, or manifold again and again. And a manifold basically is some sort of curved space which if you zoom in closely enough looks Euclidean. And you want to have a way to patch that local point of view, it's like together, so as to give you a more global view of this. And so perhaps the best way to think about in your mind, it's like what a manifold is if you imagine that you are on the surface of the sphere, or it's like say you are on the surface, it's like of the Earth, right? And the idea that somehow locally things look flat or Euclidean might be that it's like on some patch it's like of the Earth you have a chart, it's like, and you have these nice, it's like Cartesian coordinates, it's like on that chart. Okay, so you can think of that as a map, for example. So if you have a map, it's like of some local area, it's like which is a piece of the surface. And what has to happen then is that, it's like all those charts or maps, it's like have to patch together in some sort of nice smooth way. And when you do that, then it defines, it gives you a global description then of this thing which is curved. So locally you have things which are flat, but globally you have things which could be non-flat. And there has to be some sort of basically smooth way to map coordinates in one map to another map, right? So anyway, so we will discuss this again in greater detail, it's like as we go along. But suffice to say, it's like when I talk about a manifold, we're really talking about some sort of curved space, it's like which has a collection of charts, which are called atlas. So the collection of charts is called an atlas, right? And these charts have to have some sort of compatibility between them. They have to, basically, they have to have some sort of way to, you know, it's like transition. It's like from one coordinate system to another in a way which has some sort of regularity. Okay. Anyway, so let me go back to this idea of a divergence function. So it's a possibly asymmetric distance function between 2 points in a manifold. And what do I mean by asymmetric? I mean that if I have this divergence function d between points A and B, in general, that's not equal to the divergence function between B and A. Okay? And so one might ask, well, why is that the case? It's like, it just turns out that in many cases, you don't have this symmetry. Okay, but and maybe it's like sort of good examples of these is the KL divergence, which is oftentimes used in machine learning. So this is idea of this KL divergence. And the KL divergence is an example of what is called a Bragman divergence. So this is an example of a Bragman divergence. And a Bragman divergence intuitively is the following object. Okay, so the Bragman divergence is based on a given convex function. So given a convex function, we can talk about what is called the Bragman divergence. So the idea is the following. So say you have this convex function, okay, and you have 2 points which you're trying to measure the distance, okay? So let me just put one of these points here. All right. Okay. So with the first point, you can take the linear approximation of the convex function, right? And at the second point, you can measure the distance between that linearization about the first point with the actual value of the convex function. You can look at this distance, okay? And this is this is how you construct the Bragman divergence. You look at the linearization of a convex function about one point, and you evaluate that linearization at a second point, and you compare it to the convex function value at that point. Okay, so given a convex function, you construct a linear approximation at one point, and then you can look at the difference between this approximation and the value of the convex function at a second point. And in general, then, such an object, such a Bragman divergence, would have the property that this is asymmetric. So if you had done it the other way, right, what would happen is that if you swap the roles of A and B, it's like in this case, what would happen is that you would have taken the linearization at the second point and compare it to the function value at the first point. And sort of, you can just sort of see from this picture that it's quite a difference right there. So this isn't symmetric. Okay, so anyhow, right. So yeah, anyhow, yeah. So that's an example. It's like of that's a Bragman divergence. It's like and the KL divergence is an example of a Bragman divergence. And all right, so there are certain, it's like things which come out of it. So what will happen is that given a divergence function, right, you can, so this induces a metric, and in general a pair of connections of affine connections. Okay. All right. Yeah. So in the case of KL divergence, all right, the induced metric from this divergence is the Fisher-Rao metric. And you recall that I said that KL divergence is an example for Bregman divergence, and the Bragman Divergence comes from this choice of a convex function. So the corresponding convex function to KL divergence is the negative entropy. Okay, all right. Okay, so that's going to be interesting. KL divergence is somehow related to Fisher-Rao metric, and it's also related to this idea of the negative entropy. Okay, all right. So let me go back to this point. It's like I made. It's like where the divergence function induces a metric and also induces a pair of affine connections. So if you know something about Riemannian geometry, right? So if you know something sort of about Riemannian geometry, right? They're given a metric, there's some sort of canonical connection, right? There is a unique sort of metric compatible torsion free connection. Okay, which is called the Levi-Civita connection. Okay, so let me focus on this idea of metric compatible. So what does it mean for a connection to be metric compatible? Is the following. So again, you have, it's like on this curved space. Now imagine you have two vectors. Let's call them v and w, right? So given v and w at a point, you can look at the inner product between them. So v and w. And let's say you have a curve now, okay? So you can, because of the connection, you can introduce the idea of a parallel transport. So you can parallel transport these vectors. So let me sort of denote that as being, say, pi v, so pi t of v, it's like pi t of w. So you parallel transport, it's like along some sort of parametrized curve. And you can ask yourself, what is the inner product between those parallel transported vectors? And if that connection, if that notion of a parallel transport is metric compatible, then when you parallel transport those vectors and you take the inner product between them, that pair of vectors, it stays the same value. It's like as the original vectors, as the original inner product of those two vectors. Okay, all right. So why did I bring this up? So I bring this up because, it's like when we talk about divergence functions, and we said it induces a metric, we also said that it induces a pair of affine connections. So what's going on here? It's like, why is there only one, not just one? And you have, in general, a pair of affine connections which comes out of this divergence function. So the fact that you have a pair of affine connections is sort of related to the fact that the divergence function in general is asymmetric. Okay. So what happens? It's like when you do have this pair of affine connections, is there some sense in which it generalizes this notion of metric compatibility? Okay, and it does. Okay, and so basically what happens is that instead of this relationship, V and W inner product is equal to the parallel transport of V and W, you now have two different connections. Let me just call them pi and pi tilde, if you will. Okay, so what happens then is if you parallel transport the first vector with one of those affine connections, and you parallel transported the second vector with the other one, then there is this kind of metric compatibility in this way, right? You actually need both of the affine connections appropriately parallel transported in order to have that inner product stays constant along the parallel transport. So this is the sense in which these pair of affine connections are compatible with respect to the metric. Okay, so this is just a very, very quick overview of some of the geometric things which show up and which we'll discuss in greater detail. It's like as the course progresses, but hopefully that gives you a relatively high level idea of where some of the things you might have heard about before, it's like show up in the context of information geometry, how it relates, say, to Riemannian geometry, which you might have had some exposure to, and the points of departure, if you will. Okay, and as we'll see, it's like in the later part of the course, right? We'll see it's like on the one hand, it's like how you make precise sense of these objects and how they show up when you try to do inference on, it's like on information manifolds, it's like of particular classes. So with that, let me just stop here for now.